I hope you get to use your break time to a bit rest and have something to eat and drink. And so now that we are ready we will have the next session. I'm really, really delighted to introduce to you Dr. Jason Rhodes, also from the JPL. And, this is a very special session. This is not a lecture as it is, but uh, we have been very, very lucky, benefiting lots and lots of data, just downloading things. But today we're going to learn from
No,
Dr.
pues ahorita
Rhodes
la otra
how
clase,
actually
pero
people
a
work
las 2:30.
behind behind the scene before we all get data. What do people do? And so I think this is a way for us to learn the system of a network of telescopes and missions and and everything that we put our trust into getting our science going. So I'm happy to have Jason introducing us how it is in NASA in particular, and all the network that he's been involved in. So thank you for joining us, Jason. So yours now.
Okay, I'm gonna start by sharing my screen. And then I'll start my presentation. Let's see. So I hope that my screen is showing up. You can see my presentation. So someone,
yes, it's very
okay, great.
clear.
So my goal here today is to tell you about what my life is like as a NASA research scientist. And I think in the previous session, you heard from another NASA research scientist, Dita Markovic, about some of the dark energy research that she's doing. I work at JPL with Dita, but I'm not going to lecture you about the science today. Instead, I'm going to talk about what my job is and what it looks like. And most of the session, I hope, is questions from you in the audience about what a NASA research scientist does, or what my day or month or year looks like, and how we go from an idea to a mission. So I work at NASA JPL. JPL is one of about 10 NASA centers. JPL is just outside of Los Angeles, California. And the picture I'm showing here is JPL. JPL in nicer times than right now. Right now, the mountains back there are covered in smoke. There's some bad fires, but this is a particularly good air quality day we had for the picture. So back in 2002, JPL, some people high up at JPL saw that there would be a need for a space mission to study dark energy. So I was already working with JPL. I was at Caltech, and I was already working with some JPL people on a concept for a space mission that we thought might launch in about 2007. It turns out we were very naive, because we're going to launch the first space mission to study dark energy 2 years from now in 2022. But at any rate, JPL in 2004 hired me as a staff scientist. So I came to JPL to work on developing dark energy missions. So I work on a lot of different things, but the main projects I've worked on over the past 15 years at JPL are 2 missions that have as one of their primary goals to study dark energy. So one is ESA's Euclid mission. This is the mission from the ESA, which is the European Space Agency, and that's going to launch in 2022. It's an ESA-led mission, but there's important NASA contributions, 3 NASA contributions to ESA. One is the detectors, the near-infrared detectors. The second NASA contribution is NASA will do some of the data processing. When the data comes to the ground, NASA will help with that processing. And the third contribution is NASA is paying some scientists to work on the science of the Euclid mission. The second mission I'm working on is the Nancy Grace Roman Space Telescope. This is a space telescope planned to launch in 2025. It used to be, until a few months ago, be called the W-FIRST telescope, but we named it after Nancy Grace Roman this spring. Nancy Grace Roman was the first head astronomer for NASA back in 1959, and she was one of the first people to be a real champion of space telescopes. So one of the things I've learned in the past 15 years is that space missions take a lot longer to complete than I thought they did in 2004. That is, when I came to JPL in 2004, I thought, oh, it'll be only 3 or 4 or maybe at most 5 years before we launch a space mission. And instead, like I said, Euclid will launch first of these dark energy missions in 2022. So I'm going to talk here about 3 missions, 2 of which I've already mentioned, that are coming up to study dark energy in the 2020s. And these are all 3 of these are missions that I work on. So the Vera Rubin Observatory, which will do the legacy survey of space and time. That's a telescope on the ground in Chile, and it's planned to start operations in 2022. It's got a 6.5 meter mirror and will survey about 20,000 square degrees, or half of the sky. Euclid, also going to launch in 2022, has a much smaller mirror, 1.2 meters. Will survey about 15,000 square degrees, or a little over a third of the sky. W-FIRST, which is now called the Nancy Grace Roman Space Telescope, will launch in 2025. It has a mirror that's twice as big across, or 4 times the area of Euclid, or about the same size as the Hubble Space Telescope mirror. And the survey size for that is about 2,000 square degrees. So this is a mission that I've been involved with from the very start. And a mission that's, of course, very dear to me because I've been one of the people that has been working on this mission for well over a decade now. So there's some other information about these 2 space missions and 1 ground-based telescope to study dark energy down there, but I'm not going to go through all of those. This is just maybe a reference for you if you wanted to look at and compare these. So I'm going to first talk about the Nancy Grace Roman Space Telescope. So for the Nancy Grace Roman Space Telescope, I'm the JPL project scientist, the NASA JPL project scientist. The project itself is run out of Goddard Space Flight Center in Greenbelt, Maryland. So within the project, I'm a deputy project scientist. That is, there's a main project scientist at Goddard, but I'm the lead at JPL. So I'm not part of a science team investigating dark energy with Roman. And the reason is we have external people to the project that lead the science teams. So we hire people based on peer review. People propose to NASA, oh, I want to be part of this science team. And so we have a competitively selected science team. It just so happens that the lead of that science team is at JPL. I work with that science team, and Dita, who gave you the previous lecture, is a member of that science team. So one of the things I do is work with that science team at JPL. But another thing that's very important is that JPL is building the coronagraph instrument for the Roman Space Telescope. This is an instrument designed to study exoplanets, not to do dark energy. So the dark energy instrument is being built at Goddard, which is across the country in the other side of the US, where the project is headquartered. But JPL builds the coronagraph. So I'm not an expert in coronagraphs. That wasn't something I did before getting involved in W-FIRST, and now it's called Roman. But I do lead the project science team at JPL. So one of the things that has taught me is that you don't have to be the expert in the science that your mission is going to do a good job in helping develop the instrument and the missions. So I lead a science team that has experts, but I do lots of interaction with people at Goddard, JPL, external scientists, engineers, and managers, both at NASA headquarters and at JPL. So another thing that I have to do is I have to develop international partnerships. So for the Roman Space Telescope, We have contributions coming from Japan, Germany, France, and ESA, the European Space Agency. And in all of those cases, I've been one of the people that's talked to my international colleagues in those countries and helped develop the plans for what they're going to contribute. For Roman, I give about one colloquium every 2 months, meaning about 6 times a year, I'll give a colloquium at some university or lab somewhere in the world. And as I said earlier, this is a lot of interaction and coordinating between scientists and engineers to help define what the requirements are on the mission and the telescope and the instruments. I'm not doing a lot of the science preparation itself for Roman because I'm the one or one of the people that's helping coordinate that. So for the ESA Euclid mission, I was one of the key people over a decade ago, between about 2006 and 2012, to help convince NASA that it was worthwhile for NASA to participate in the ESA Euclid mission. That is, for NASA to put money in to buy infrared detectors and pay scientists to participate. So when NASA decided to join, even though I was the person that had convinced NASA to do that, NASA ran a competition to decide who would be the lead of the science team that they were developing. And I won that competition. So I have a science team with about 60 people in the US who are funded by NASA to work on Euclid science. And this includes Dita, who gave you the previous lecture on dark energy earlier today. And so this is a different job than what I do on the Roman Space Telescope. And it's different because on Roman, I'm the project scientist. So I'm the one that coordinates between the science teams and the engineers. But on Euclid, I run the science team for NASA. So I have a couple of other jobs in Euclid. I'm the NASA representative to ESA for Euclid. That is, ESA, the European Space Agency, has meetings every few months about how the progress with Euclid is going and whether the science is being developed correctly and so on. So I travel to ESA or other parts of Europe to represent NASA at those meetings. And there's about over 1,000 scientists and engineers around the world working on Euclid. And they're members of what's called the Euclid Consortium, these 1,000 people. And there's a board of people, about 20 people, who are the governing body of Euclid. And there's a representative from each country in this Euclid Consortium board. And I'm the NASA representative on that Euclid Consortium board. And that's the Euclid Consortium board is really the highest authority in Euclid that sets the strategic direction of what Euclid is going to do. So I'm the deputy chair of the board. That is, there's a chair who runs the board. I'm his deputy. And in 2022, I'll begin a 2-year term as chair of the Euclid Consortium board. So I'll have a very high up role in Euclid, helping to define the vision and run the mission. So the third project I talked about is a ground-based telescope, the Vera Rubin Observatory. I'm not very involved in that, but one of the things that we are recognizing in the dark energy community is that we're going to do a better job in understanding dark energy if we coordinate how we process and analyze the data from the Roman telescope, the Euclid telescope, and the Vera Rubin Observatory. And so I'm the liaison. I am the connection between Roman and the Vera Rubin Observatory and Euclid and the Vera Rubin Observatory. Also, there's a spokesperson for the dark energy portion of the Vera Rubin Observatory survey. That spokesperson is elected by all the scientists. And that spokesperson, she has set up an advisory board to advise her on various aspects. And she has asked me to chair that advisory board. So I'm more of an advisor to people in the Vera Rubin Observatory project rather than doing a lot of the work myself. So a few other things that I work on. I have several postdocs, between 2 and 4 at any one time, that I oversee and help. They're very independent because, as you might imagine, I'm quite busy with all these other project roles, but I meet with them regularly. I'm helping to develop a UV telescope. This would be led by Canada. The name of the telescope is Castor. You could Google this to see what's planned. I'm the JPL lead for the SuperBit. That's a super pressure balloon imaging telescope. And that's what I'm showing in the picture here. I'm not in the picture, but that's a picture of people with this telescope that's going to be launched from a balloon. And JPL is taking part in the science of that. Most recently, I've been helping some people at JPL develop ideas for quantum mechanics experiments in space that might be able to detect dark energy. And we have a mission idea that's not approved, neither is Castor. These are mission concepts that we might eventually get approved to build. And that mission concept is called Goddess. And you can probably Google that too. So I have just a couple slides left. And so this is a fairly typical day for me. This is my calendar. And so I can just step through a few of the things, and you see that sometimes I have more than one meeting at a time, and so I have to choose which one to go to. So my day on this particular day starts at 7 a.m. I have a telecon with some Euclid people about weak gravitational lensing. Weak lensing, that's what the WL stands for. That is a technique to study dark energy. Then I have a little break. I usually try to eat breakfast in that little break. And then I meet with Agnes, who's one of my postdocs, and I meet with her every week. And then the next 2-hour block is a meeting for all of the people that are in the core group helping to define the coronagraph for W first. And there's also a group meeting to talk about detectors on W first, Roman. And I'm not able to go to that if I go to the other meeting. And then I have a meeting with Eric, who's a colleague at JPL. I have a meeting with Peter, my postdoc, and so on. And you can see that the day is filled up from 7 to 4:30 with meetings with people, colleagues, or meetings about projects, Euclid, or W First Roman. And so you can imagine this is one of my busier days, but all days have quite a few meetings. And so I don't have a lot of time to just sit down and do science. And this is one of the reasons I have postdocs working with me. They're the ones that do a lot of science. I'm more of a coordinator for the work that they're doing. And so the last thing I'll talk about, my last slide. So this was a typical travel, and I say in the before times. Obviously, we're not traveling right now because of COVID. I don't even go into work. All my meetings are virtual. And while I'd love to be there with you in Indonesia, and I hope to someday come back to Indonesia, I've been once, it's just not safe to travel right now. But last fall, in October, November, and December, this is what my travel looked like. So I went to Japan for 2 weeks to work with some people on some science, and also to talk to people about joining the Roman Space Telescope. And a little bit, we talked about them joining the Euclid Space Telescope. Then I went to Paris for a Euclid board meeting. And then in the same month, I went to Maryland to Goddard Space Flight Center for a review for the Roman Space Telescope. So I wasn't even home here in California very much in October at all. In November, I went for a week to a meeting about the Subaru telescope, which is a ground-based telescope in Hawaii. That's a Japanese-owned telescope, but it sits in Hawaii. And I went to a conference there. And then December, I went back to Europe again for a meeting with the ESA Euclid science team in the Netherlands. So my typical year has me going to Europe usually about 8 times, 6 to 8 times, and going to Japan usually once. And then in the last few years, I've gone to Australia about once a year. And all of these places are places where I work with colleagues and have meetings with colleagues. And then I have various trips in the US, either to give colloquia or to go to Goddard Space Flight Center to meet with people about Roman. So that was all the slides that I had. And so what I'd really like to do is I'd like to hear what questions you have about anything I've shown you here, or about how missions are developed. And so I don't know how they want to coordinate the questions, but I'm open for questions now.
Thank you very much, Jason. It was a nice, quick overview of how things are going behind the scenes. It's awfully busy. You know, your schedule is pretty dizzying, I think, and it's admirable how you manage everything to be going at, you know, at the same time with many projects. Okay, you've got lots of questions lining up for you.
Okay.
Let me just read, and I think I open the opportunity for people to ask questions directly, but to just get things going. Okay, here's the first one from Naman Bajai from India. Is there any way we, students from different Asian countries, be a part of JPL missions, mostly for a short period of time during our graduation studies?
So that's a great question. So there are different phases of missions. So for instance, when Roman is launched, the Roman Space Telescope, the data will be worldwide public almost immediately after it's taken. There won't be any what we call proprietary period. So anyone in the world will be able to download the data and do science on it. And so if you wanted to be part of analyzing the data from Roman, you could just work with your advisor to do that. For Euclid, there's a approximately 2-year proprietary period where the data wouldn't be public for 2 more years. Now, if you are asking more immediately something about how do you get involved in the planning of the missions before they happen, that's a bit more difficult. But I would say if you are connected with an advisor who has a connection or a research connection with someone at JPL or someone working on a NASA mission, that's the easiest way to do that. There are also some graduate student fellowships, but you typically have to be at a US institution rather than in another country to get those. So I would say work with your advisor and see if your advisor has some connection to people working on the missions. Let's see. Should I go to the next question?
Yeah, if you could access them, that would be great. Thank you.
Yeah. Has there ever been a mission or an instrument proposal was scrapped because the engineering team found it impossible? Or does the science team know the engineering limits well enough when they're creating a mission proposal? So the answer to that, let me work backwards. The science team often does not know the engineering limits when they're creating a mission proposal. And so science teams can and often do propose things that are challenging. Now, certainly, I think the science teams wouldn't propose something that breaks the laws of physics. The science teams know better than that. But anything that doesn't break the law of physics, I would say at JPL, the engineers would not say it's impossible. They would say it's possible. And so typically why things wouldn't move ahead is not because that they're impossible, it's because they're too expensive. So you could imagine proposing something that was so challenging, it would cost too much money. And so when NASA develops missions, it has different classes of missions. And I'll give you some idea what the classes are. So for a few $1 million, you have these types of balloon missions and sometimes sounding rockets that go into space and then come back down. So for NASA just introduced a new class of mission called a Pioneer class of mission. And these are about $15 to $20 million. And they would be probably a very small satellite. The next class of mission above that is an Explorer class of mission. That's a few $100 million. That's probably something like the Castor telescope in Canada I talked about. The next Explorer that NASA will launch is called Sphere-X. And that's one you could Google, S-P-H-E-R-E, Sphere, and then the letter X. Beyond that, there are probe class missions. Those are missions that cost less than $1 billion. Most recent probe class mission NASA did was the Kepler Space Telescope. And then the biggest missions are called flagship missions, the James Webb Space Telescope, Hubble Space Telescope, and the Roman Space Telescope. So you have different classes of missions. And so the more challenging and expensive something is, it goes into a bigger class. And so what usually happens is the scientists and engineers get together and they try to figure out how much something costs, and then they try to scope it into the appropriate class. And so what you might end up having is, if the science is compelling enough, you might have an idea that could be a flagship class mission. But if it takes flagship class dollars to do science that's only worth less, that might be something that doesn't go ahead. So another thing that we do at JPL that's really exciting is we have what's called an A-team exercise. And that's, we have a team of engineers at JPL, engineers and managers, and their whole job is to get together a group of scientists and a group of engineers and spend maybe 2 days brainstorming an idea for a mission or a survey or an instrument. And usually at the end of that 2 days, if they have the right scientists and engineers in the room, they have a pretty good idea of whether something is going to be feasible within a certain cost. And I don't know how many, but JPL probably runs about 50 or more of these sessions every year across all science areas, astrophysics, planetary science, and so on. And so these are really exciting, really draining. They're very tiring sessions because you spend 2 whole days just brainstorming and trying to knock out an idea for a mission. Let's see. Will the WFIRST telescope be brought back to Earth if the mission is completed? No, it will not be brought back to Earth. It's going to be launched to L2, which is the Earth-Sun Lagrange point. It's a point of stable gravity, and it's well beyond the orbit of the moon. It's several times further away than the moon. So it's going to be very far away. Another exciting thing about the Roman Space Telescope is we're designing it to be serviceable, and the easiest servicing you can do of a telescope like that is you could refuel it. So it takes a little bit of fuel to keep it going and move it. And so we could imagine that if we refueled it, the Roman Space Telescope might be able to continue doing science for 20 or 30 years, like the Hubble Space Telescope has. And so we would just hope to keep it running for as long as we can. And if when it's done and we aren't going to run it anymore, we would just leave it at L2. We won't be able to bring it back to Earth. So what took Roman so long, WFIRST so long to be built? That's a great question. And really the answer is money, funding issues. So as you may have read about, NASA has the James Webb Space Telescope. That's a space telescope that was first proposed in the 1990s and is going to be launched hopefully next year in 2021. But it's really exploded in terms of its cost and its schedule. And so that has prevented us from working as much on Roman WFIRST as we wanted to, and that's pushed out the funding for Roman WFIRST till later. And it's only in the past couple years we've been able to have enough funding for Roman and WFIRST to move ahead towards launch. So it's really mostly a funding issue. There are always some engineering issues. but those can usually be overcome. Sometimes there's delays of months or even years, but it's really funding that's the biggest stumbling block. And part of that is because enough effort with enough engineers will usually solve any engineering problem. It's just finding the money to pay them. And so the last part of the question was, is it science itself that's delaying the missions? And the answer is really no, it's never the science. The science is always ready to go. And in fact, that's the first thing. So without compelling science and a compelling science case, a mission will never move ahead. So the science is sort of the first thing that's ready to go on a telescope. Let's see. I would like to know the step about how mission ideas in NASA is selected until the development, until the deployment. And can you tell me about funding such a mission? Is it entirely from the government or another source? So NASA missions are always funded entirely by NASA. For the ground-based telescopes, sometimes there's other government agencies or private money coming in, but NASA missions are always funded by NASA. So there's several ways that NASA gets missions selected. So for the smaller missions, that is missions that cost $5 million, $20 million, or even several $100 million, there's a competition and anyone can put in a proposal and then it's evaluated. Now, for the larger sizes of those, the Explorer missions that are about 200 or 300 million, the proposal to do that, the initial proposal can be like 1,000 pages long. So these proposals cost millions of dollars to put together and are very, very intricate and complete. But these are proposals that are evaluated by NASA. So that's how those missions are selected. For the biggest missions, the flagship level missions, they're selected by what's called a decadal survey. And decadal is from the word decade, so 10 years. So every 10 years, there's an astronomy decadal survey in the US, which recommends, it always has recommended a big flagship mission. First decadal survey was in the 1970s and recommended the Hubble Space Telescope, which was eventually launched in the 1990s. And since then, it's been usually about 20 years between the recommendation and the telescope flying. So in the 80s, there was a recommendation for, I think, Chandra telescope, an X-ray telescope. In the 90s, the recommendation was Spitzer. In 2000, the recommendation was the James Webb Space Telescope, which will be launched next year. 2010, the recommendation was WFIRST, which is now the Roman Space Telescope, be launched in 5 years. So it'll take 15 years to launch. And now it's 2020, so there's another decadal survey happening right now, and it's examining 4 different concepts for flagship missions that NASA would hope to launch in 2035. So already we're thinking about what missions we're going to launch in the 2030s. Let's see, are there instances of a project being pushed behind the schedule due to unforeseen technical issues? Yes, lots of those. The more complex the mission, the more likely that technical issues will come up. The best example of that is probably the James Webb Space Telescope, which was originally supposed to launch 10 years ago, and it's still not launched, and it's going to launch hopefully in 1 year. It's been because wasn't enough funding always to solve all the technical problems that came up. And if you know anything about the James Webb Space Telescope, you might know that it's a very technically complex space telescope because it's going to be 6.5 meters across, and that's too big to just fit in a rocket like that. It's also going to have a sunshade to keep it cool that's going to be several tens of meters across. And so both of those, the telescope and the sunshade, have to fold up, and then when they get to space, they unfold. And so designing and then testing that so that it happens to work exactly correctly has been a very big technical challenge for the James Webb Space Telescope, and one that's taken longer to solve than NASA thought it would. And that happens quite often, that technical problems make a mission take longer and cost more. And the way we try to solve that is we add in something called reserves or contingency to the cost of a space mission. And what I mean by that is, if you propose a space mission to NASA for $5 million or 20 million or $1 billion, what you do is you add up all the cost of developing all the parts and all the science, and you add up all the costs that you think it's going to cost, and then you add to that, you add about 30%. So if you said, okay, we think it'll cost us, $200 million to build this, and you have a very detailed list of what would go into that 200 million, you would have to take 30% of that, or about 65 million, and say, we propose to NASA that we need 265 million to build this, because there's always going to be some unforeseen technical challenges. So you always have to have extra money. And so how the problems occur is if we have problems that go beyond that 30% extra we add in. And that's, of course, what's happened with something like the James Webb Space Telescope. Is there an opportunity for physics teachers, STEM educators from Indonesia and Asia to get training in a workshop in JPL Caltech? There is an opportunity to do that. There's several programs. So there's a summer program where they bring in STEM educators to IPAC every summer, which is a part of Caltech. It's where they process the data from space telescopes like the Spitzer Space Telescope. So if you Google that and you can't find the link, because I don't have it, I can't remember quite the name of the program, please contact me or have Pramana contact me, because there is a great program to bring physics and astronomy educators in. While I've never done it myself, I've heard only really good things about it. And I think one of the opportunities you would have if you came to Caltech to do a workshop like that is an opportunity to tour JPL. So Caltech and JPL are affiliated, but JPL is about 10 kilometers away from Caltech. So you're not right there, but you could take a tour of JPL. And JPL is a really fascinating place to take a tour. I think people know that we just launched another rover to Mars just a few months ago, and all successful Mars rovers have come from JPL. And so we have models of these Mars rovers, and if you come to JPL, you can see the control center where they're driving these rovers around Mars. So it's a really exciting place to take a tour. So again, if you don't find that link, let me know. Let's see, if the telescope has a problem after launch, how does NASA solve the problem? Well, that depends on the telescope. For instance, the Hubble Space Telescope, we sent astronauts to fix the problem. The astronauts fixed the problem that was initially there. But then there was also astronauts sent to Hubble to upgrade it, put better instruments on. So it was launched in 1990, but we kept sending astronauts to put better and more capable instruments. Now, since then, we don't have the capability, because we don't have the space shuttle anymore, to send astronauts to space telescopes. But there's several groups that are developing plans to make robotic servicing of telescopes a possibility. And while the James Webb Space Telescope doesn't have this possibility, other space telescopes, including Rubin, are built with the idea that they might be serviced by robots. there are options for servicing telescopes, but I think the real answer is this. It is unlikely we would be able to fix a telescope that is in space already if something goes wrong with it. And so what we do when we build a space telescope is we test and test and test, and we test over and over. And so you could imagine, let's take a camera. So a camera has a number of individual detectors. So we would test each detector, and then we would put all the detectors together, and we would test all the detectors together. And then we would put the detectors, all of them, into a camera, and we would test the camera. And then we would put the camera into the spacecraft, and we would test that. So we test at component level, that's like the detector, and then we test as we integrate, as we put things together, we test at system level. And so there's testing and testing and testing over and over and over. And this is what causes a lot of the cost for space missions and the time it takes to complete, because we just can't go up and fix these telescopes. And so we do lots and lots of testing to make sure that they're they're as robust as possible. So how much does NASA dedicate for this problem of solving space pollution? That's not really my area of expertise. I know there are people thinking about that at NASA. So that's a big concern, especially for a low Earth orbit. There's lots of stuff from old satellites and so on. We don't worry about that so much at L2, where we're sending the Roman Space Telescope, the Euclid Space Telescope, and the James Webb Space Telescope. So that's not something we worry about there, but it is something that NASA and other space agencies are concerned about with low Earth orbit. Let's see, I have a dream to visit JPL, NASA in the future. I can tell you that in addition to, if you're ever gonna come to the Pasadena area or Los Angeles area, you can sign up for free JPL tours. And these are really, really great tours. They have a professional tour guide that will take you through. These tours fill up months in advance. And so if you're planning a trip to Pasadena a few months or many months away, you should check on the JPL website if the tour is available. And I can tell you, yeah, JPL is a really fun place to work and a fun place to tour. So for Euclid mission, will there be a consortium for data processing and data analysis? And the answer is yes. So we have a Euclid consortium already, and that Euclid consortium has really three jobs: to provide the instruments. That's two cameras. There's two cameras on Euclid: a visible camera and a infrared camera. And the infrared camera is the one that the US provided detectors for. NASA provided those detectors. So providing these instruments. The second job of the Euclid Consortium is to process the data when it gets to the ground. And the third job of the Euclid Consortium is to do the science with the data. So that's a consortium that's available to people in the US, Canada, Japan, and European countries. But I mentioned this before, and I'll mention it again. The Euclid data, after a couple years, will be public to everyone in the world. And so it'll be processed and then made available to everyone in the world. Is there any other body in where the chances of stable life has been found? So we have a number of places where we're looking for life in the solar system. And the goal for looking for life in the solar system is to find and follow water. So we look on Mars because we know that there was a lot of liquid water on Mars in the past. We look on Europa and moon of Jupiter, and Enceladus, a moon of Saturn. These are moons that have liquid water under a crust of ice. JPL has plans to send a probe to Europa in just a few years, in the early 2020s. And that's a precursor to eventually sending a probe that might land on Europa or land on Enceladus and look for life and signs of life there. So that's one way. So the other way NASA is looking for signs of life is we're building instruments like the coronagraph that's going to go on the Roman Space Telescope. And the coronagraph is an instrument that allows us to directly image exoplanets, planets outside of our solar system. And if you build a powerful enough coronagraph, you can look at the atmosphere of a planet. And while we won't have quite a powerful enough one on Roman to do this, the next generation of coronagraphs after that, perhaps in the 2030s, would be powerful enough to look for signs of life on an Earth-like planet around a sun-like star. And what you do is you look at the atmosphere of these planets and you look for non-equilibrium chemistry. For instance, you look for oxygen, which we think is a byproduct of life. If you were to look at Earth from far away and you would look at our atmosphere, you would say something is replenishing the oxygen in the atmosphere. Because as we know, oxygen is a very reactive molecule. Oxygen wants to combine with things, either fire, things burn, rust, metal rusts with oxygen. And so we would see oxygen combining, but something is putting the oxygen back into our atmosphere. That's life that's doing that on Earth. So we would look for that type of thing around planets outside of our solar system. And so the next question was, you'd like to study exoplanets, how we select a suitable mission. So two of the missions that are being examined by the 2020 Decadal Survey for perhaps flying in the 2030s have as one of their primary goals looking at exoplanets to look for signs of life. And these two missions, one is called LUVOIR, that's Large UV Optical Infrared Telescope, and the other is called HABEX, that's the Habitable Exoplanet Telescope. Both of these telescopes would have a coronagraph, similar to the one we're building for the Roman Space Telescope. And in fact, both of these telescopes depend on the Roman Space Telescope to develop the technology for a coronagraph that would be powerful enough for them. So with the Roman Space Telescope, we're going to fly a coronagraph that tests a bunch of new technologies that might be used in the 2030s. Have there been projects where in the end they perform underwhelmingly? If so, what do you do about them? So I think I can't really think of NASA projects that have performed underwhelmingly. The reason is I think it's so competitive to build, it's so competitive to compete for the slot to build a NASA mission that if they don't fail for some technical reason, which does happen, it rarely happens, but it does occasionally happen, then the science is always really, really exciting because there's been so much reviewing of the science and competitiveness of the science. Let's see, the next question is, can I say something about a human mission to Mars? So a human mission to Mars has always, in my lifetime, been 20 to 25 years away. And I think it's still 20 maybe years away. And the reason is it's going to be very, very expensive. And so the human side of NASA exploration has just never had enough money to put together everything that's needed for a human mission to Mars. But what we are doing leading at JPL is these robotic missions to Mars, like the upcoming Mars rover that we just launched this summer, just a few months ago, that are looking more and more at Mars, and they're really a precursor to any human mission to Mars, telling NASA or other space agencies, where would be the best place to send humans on Mars in order to look for life and better understand Mars. So we're doing a lot of work with robots to get ready for an eventual human mission to Mars, but I think that's still probably a long way away. How often do NASA scientists who are working on observations communicate with theoretical scientists, and how is such collaboration going in NASA? So we really, on a science team, like for the Roman Space Telescope or even the Euclid Space Telescope, we have scientists who work with data, and we have scientists who are theorists, and we have lots and lots of meetings and discussions. And I probably talk to theorists once every couple of weeks about these missions. And in fact, one of the things that I like to do is when I hire postdocs at JPL, I like to hire postdocs who know quite a bit about theory, because me and a lot of my colleagues are more on the data side and developing missions. So it's very good for us to have theoretical colleagues, and especially at the postdoc level, because theory is something that is changing all the time. And so when you get younger, early career people coming, they're bringing in the latest and newest ideas. Let's see, is there any possibility that life can be made up of inorganics? I think it's possible, and that's not my area of expertise. But what we're doing at NASA is we're trying to take a path to looking for life that would be similar to life on Earth, because that's the life that we know and we've seen. And so really, I think the mantra for that would be follow the water. As I said before, we're looking for water on bodies in the solar system. We're looking for water in the atmospheres of exoplanets and so on. So it's possible that there could be life that's inorganic. We just don't know yet. Has NASA or any other major organization been trying to tackle the issues of satellite networks like Starlink? And so if people aren't familiar with this, Starlink is a project of SpaceX, which is here in Los Angeles. SpaceX launched people to the space station earlier this year, but SpaceX is launching many small, very small, about 15 or 20 centimeters across satellites to provide internet service. But one of the things these satellites do, of course, is they reflect light, and especially for ground-based telescopes, this can be a problem because you see streaks of light at the beginning and end of a night. That is, if you're looking close to the horizon, you're seeing close to the horizon when the sun is just above or below the horizon, you're seeing reflections off of these telescopes. So this is a real problem for ground-based telescopes. And I know, for instance, the Vera Rubin Observatory, the one that I mentioned that I work on a little bit, they are taking a very active role in negotiations and discussions with SpaceX about how to make this better. One of the ways could be that they could paint these satellites black. I'm not sure what other things that they're talking about, but this is not something that NASA has been very active in, because NASA is in the business of putting telescopes in space. And so NASA leaves it to other government agencies and other projects to worry about that ground-based telescope problems like the Starlink. When there's a failure in planning and construction, is there any leeway in the budget and timeline? And also, if there is an accident or hardware malfunction, are there any ramifications to future missions and collaborations? So those are two great questions. So first of all, when I mentioned before that we add 30% extra money, it's to deal with failures in planning or construction and that sort of thing. So there's supposed to be extra money in space missions that is ready to take care of these things. And we, in addition to adding 30% extra money, we actually add 30%, typically is a number we add in extra time. That is, if we say, okay, all of these things we need to do, this will take a week, this will take a week, everything added up takes 100 weeks. We would say, okay, if it takes 100 weeks, we're gonna budget that we have 130 weeks to do this. But sometimes even that is not enough. And so we have to have delays. And so if that happens, often what happens is the mission, the manager of the mission will have to go to NASA and we'll have to have a review. And NASA will say, okay, what happened? How much more is it going to cost? And then NASA has to make a choice. Are we going to give them the extra money, or are we going to cancel the mission? And in some cases, NASA has canceled missions if people fall behind in budget or timeline. So it just depends. NASA has to decide, is it still worth it or not? And if there is an accident or hardware malfunction, are there ramifications for future missions and collaborations? Certainly there are, in sort of two ways. One way is that if something fails and they're planning that for a future mission, that future mission has to say, okay, we have to find a new way because this failed, we can't fly it again. And so it will cost them money. Or the other way things can affect future missions is if NASA decides that this mission that's had a problem needs more money, they can give that money to that mission. And that means a future mission might not get selected or might be delayed. And so that's, for instance, something that's happened with the James Webb Space Telescope. They've been getting more and more money, and that's meant we've had to wait longer and longer to get WFIRST, Roman, started. So it does have ramifications if things fall behind. Let's see. Since missions take so long, is it possible that the science community has moved on from a certain topic when the mission finally launches? Does this mean the newer theory ideas have a harder time getting missions? So that's two very great questions. So first of all, I think, again, in the process of trying to select a mission, NASA and the people NASA hires to select and evaluate mission proposals really try to think about, okay, what's going to be the most compelling science when this mission flies, whether that's in 2 years or 5 years or 15 years. And so if you look at something like the decadal survey happening now for these flagship missions, they're trying to take into account what's happening theoretically, what's happening in ground-based telescopes, the fact that pretty soon we're going to have several 30-meter ground-based telescopes to evaluate what the big questions will be in the mid-2030s. The other thing that we try to do at NASA is we try to build robust capability into the missions. And certainly that's something we've done with the Roman Space Telescope. So the Roman Space Telescope, when it launches in 2025, we'll be able to change the surveys that it does and do different types of observations because it's a very capable telescope. And we'll base those on what's the best thing for Roman to do in 2025 rather than what was the most compelling thing in 2010 when we started to plan the telescope. And so the other part of the question, does this mean that newer ideas and theories have a harder time getting missions? I think in a way it probably does. A theory or idea has to be developed for a few years at least and has to be stand the test of time. The other thing that you have to do if you want to get a NASA space mission is you have to somehow show I did everything I could to solve this science problem using ground-based telescopes. So if I can solve a problem using a ground-based telescope, even if it would take a long time or be expensive on that telescope, NASA will say, okay, you should solve the problem on the ground. NASA only wants to do those things that have to be done in space. So why do we need so many different space telescopes? Why not put everything together into a flagship mission like James Webb Space Telescope? Well, I think one of the easiest ways to think about this is the Hubble Space Telescope has been in orbit for 30 years now, been operating for 30 years. In that time, it has surveyed probably about 25 square degrees of the sky. And just for your reference, the whole sky, the entire sky is about 40,000 square degrees. So it's surveyed, Hubble has surveyed about 25 of those 40,000 square degrees. And James Webb in its lifetime will probably be able to survey something like 10 or 20 square degrees of the sky, much, much deeper, much higher resolution than Hubble, but that's it. Now, something like WFIRST, Roman, will survey several thousand square degrees of the sky. Now, it won't do it as deep or as high resolution as the James Webb Space Telescope, but it will do it, Roman will do this 2,000 square degrees at the same resolution that Hubble does and the same depth. So it'll do things that Hubble has done, but it'll do them over hundreds of times more area of the sky. So one of the reasons we need multiple space telescopes is some telescopes are designed to go very, very deep over a small area of the sky. Some telescopes are designed to go less deep over bigger areas of the sky. The other reason we would want to build different space telescopes is we have different types of instruments. Some space telescopes do imaging, some do spectroscopy, they take spectra, and of course we have telescopes in the UV, ultraviolet, the optical, the infrared, all the way out to gamma rays. We have X-ray space telescopes. So we have space telescopes at different wavelength ranges. And so it all depends on the science and the capability you need for the science. Is NASA planning to have any manned missions on the moon? Which one of the human missions is beneficial in this era? So NASA has plans to send people back to the moon within the next decade. One of the issues with doing something like that is just like with going to Mars, it's very, very expensive to send people into space and even more expensive to send them away from Earth orbit to the moon or to Mars. Has just not been able to have enough money to have very. I got muted. Can people still hear me?
Yes, still hear you.
Okay, great. So
yes, I can hear.
Okay, great. So in order to I think get people to the moon or get people to Mars, we just need to have more money available at NASA, because while we can send probes to the moon and send probes to Mars, it's much more expensive to send people because of two reasons. One, you have to keep them alive the whole time. You have to take all the supplies they need. And two, you have to bring them back. So that's also expensive. So that's, I think, I hope, did I miss any questions that were in the chat?
I think you're doing great, Jason.
Okay.
Thank you very, very much. I think we've got a few more minutes if anybody else would add a few questions, and if Jason wouldn't mind taking.
I don't mind. Yeah, I'm having a great time, and these are really fantastic questions, and I really do hope some of you have a chance to come work at JPL or visit JPL. And if you ever do, look me up and send me an email, and I'd love to meet you if you're ever at JPL. But please, if there are more questions, I'm happy to answer them.
So please, everyone, we have time for a couple of more questions. While waiting, I probably use the chance to ask my question. Oh, there's one coming.
Okay. if a new technology that could be more useful for observations is developed while you're constructing a mission with an older technology, you change the design to incorporate the new technology for a future project. So the answer is no, we don't change the design. So whatever we fly, the technology is frozen at least 5 years before we fly it for the bigger missions, and often more like 10 years before we fly it, the technology is frozen, between 5 and 10 years. And even if there's a new technology, we don't change it because it becomes very expensive to change things. And it also introduces a risk because we're doing lots and lots of testing. As I said, we test first at the component level and then at a bigger level. And every time we put something together, we test everything together. And so you can't just swap in a new technology because you'd have to start your whole test chain again. So really the idea is if you have a really compelling new technology, you use that as the basis for a future project, not the one that you're sort of in the middle or late stages. Okay, so if a mission like James Webb Space Telescope get canceled, it remains a high priority. Wouldn't this mean that the next massive mission should be basically doing the same thing? So how catastrophic must mission prep be for a flagship to be completely canceled? These are great questions, yes. So first of all, if we've never had a big flagship mission get canceled. I think if something like James Webb Space Telescope got canceled, there's still enough compelling science that we would want to do something similar to James Webb Space Telescope. We might make different design choices or try to do something different if it ended up getting canceled. I don't think that James Webb Space Telescope will get canceled, but if just using that as an example. On the smaller missions where you sometimes have gotten missions canceled, they do in fact then they don't just automatically say, well, we still think that's the most compelling science. They do a complete competition to see what the next mission should be, and if that still is the best science goal. And how catastrophic must a mission prep be for a flagship to be completely canceled? We don't have, I don't have an answer to that. And the reason I don't have an answer to that is that we've never had a flagship mission be canceled. And the James Webb Space Telescope has exceeded its budget by many, many times and been pushed out by many years from its original launch and still not been canceled. So I don't know what the threshold for canceling a flagship would be because it's never happened. Was the Voyagers belong to NASA? And could I say something about Voyagers? Yes. So the Voyagers are NASA missions that have now exited the solar system. So these are the things that are the furthest away from the sun that we've ever made. And in fact, the Voyagers come from JPL, where I work. They were launched in the 1970s, and the Voyagers are still working. That is, they are still sending back data to us at JPL. And one of the interesting things that they found in the last few years is that the Voyagers have gone from where most of the particles they see are from the sun to where most of the particles they see are from the galaxy outside of our solar system. And so they've gone past the edge of what we consider our solar system. And we're getting that data back. It's very weak signal, but we're getting it from what's called the Deep Space Network. And the Deep Space Network is a series of 3 antennas, huge antennas, many tens of meters, I think 40 meters across each antenna, spread around the world. There's one in the desert here in California. There's one in Spain, and there's one in Australia. So if you look out in space, there's always one part of the Earth where a very, very distant spacecraft could communicate back to the Earth. So these Voyagers, as I said, were launched in the 1970s. but they're still working, sending back a little bit of data, and that's pretty exciting. Is there any plan to construct a NASA instrument on the moon? If yes, so how long would it likely take? Right now, our plans at NASA are not to construct a base on the moon, but rather to construct a space station that orbits the moon, and we call this the Lunar Gateway. And then the idea would be to have astronauts go from this Lunar Gateway down to the moon, stay for a little while, then come back to the gateway. I think this would probably take, if there's enough funding, it would probably take about 10 years to construct that, but I don't know if there's enough funding to do that. Let's see, some of the missions get very emotionally attached to the people, like the end of Cassini. Can you please share experience like this if I got emotional for a certain mission? Well, I just saw a talk by one of the Cassini scientists about when she watched the last day of Cassini. Cassini was a mission to Saturn, and when it was done with the mission, they didn't want the spacecraft flying into one of the moons of Saturn that had potential for life, because it wasn't sterilized. So they ended up crashing it deliberately into Saturn. And when she was telling us about this, she started tearing up and crying because she'd been involved with Cassini for so long and was so emotionally attached, just like you say. Now, for me, the missions that I work on and have worked on developing since 2002 have not flown yet. So I'm still waiting for a mission to fly in space where I have that emotional attachment. But certainly with the Euclid telescope and the Roman space telescope, I will have that emotional attachment. And when they reach the end of their life in 2030, I think it's very possible that I'll shed a tear too and be sad to see these missions end. So in NASA, do we have collaborating projects with other countries, space agencies like JAXA, Japan, China, and Russia? So the answer is, yeah, we have lots of collaborations with JAXA. And in fact, I travel to Japan to talk to colleagues at JAXA about once a year. NASA is involved in a number of projects with JAXA, including the Roman Space Telescope. And there's a Japanese mission called XRISM. It's an X-ray mission, XRISM, and NASA has a big component of that mission as well. So that's really NASA collaborating on JAXA missions and JAXA collaborating on NASA missions. With China, we have very little collaboration, and that's by design. China is seen as more of an adversary to the US than someone we want to collaborate with on space technology. And so at NASA, we're really not allowed to collaborate directly with China. And we have some collaborations with Russia, especially like the space station. That's a big collaboration with Russia. There's less of that in astronomy. We don't have a lot of astronomy collaborations with Russia, but we certainly do with JAXA, Japan. And I should also say we have collaborations with ISRO, that's the Indian Space Agency. We had, I think just recently, we had a collaboration with the United Arab Emirates. We have collaborations with Qatar, let's see, Canada, and space agencies all across Europe. So we have quite a few collaborations across many international partners. And KAZI, which is the Korean Space Agency as well.
Wow, thank you, Jason. Lots of really perceptive questions, I would say, about, very genuine interest. And I don't know whether more are coming, but.
Yeah, these have been really fantastic questions, and I'm actually really impressed with the level and depth of the questions.
Yeah, yeah. Well, perhaps if I may add mine in there.
Yeah,
many of us, you know, we're coming from countries which are gearing up into astronomy, and then, you know, building instruments and facilities, and most with, you know, just a few meter optical telescope about that size. Now to get ourselves propelled forward into the current science frontier, how do we what would be the wisest investment? Would, you know, do a science project with you, and then a follow-up ground-based observation, you know, closely uh, 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 connected with your upcoming missions data, or should we be part of a consortium? And how do we go about it? How, who should we talk to?
Yeah, okay, so there's the question, I think, is how do scientists and people in general, maybe not just scientists, maybe engineers as well, in countries with developing space programs, how do they get involved in NASA missions? So there's, I think the easiest way is on a scientist to scientist basis. Find a scientist who's working on the area of science or working on the NASA mission, and start talking to that person. Now, I think that's easier than trying to do it at a national agency level. Right. So even if your country has a space agency, for instance, on the Roman Space Telescope, NASA really doesn't want to have a collaboration with a foreign space agency unless what they're providing is worth maybe $20 million. So it's a pretty big number to have to be providing something from a country. And that would usually not be providing scientists, it'd be providing some physical engineering component. And the reason NASA has sort of such a high level of wanting to have some official collaboration is, one, there's always a cost in terms of interface. And if I can give you an example, for NASA, I'm the representative to Euclid, and I have to go to Europe probably 6 or 8 times a year, as I said before, and there's a cost, you know, to that in my time, and NASA has to pay for my flights. And so if they're not getting a lot of value, you need to make sure that that interface isn't costing more than what's valued. And also, it's always seen as a risk to have a foreign partner, because you never know if they have budget problems or something, they might not be able to deliver what they promised. So rather than having an official collaboration between agencies, I think the easier way to go is to try to find the appropriate scientists and make that scientist to scientist level collaboration. Now, I think that should get easier in the future, and because one of the side effects that I think we've seen of COVID-19 is people have seen that they don't have to travel everywhere to interact with people. And so, you know, while I would love to come to Indonesia, if you had said, oh, can you come to Indonesia to give this talk, I might have been able to, or I might not, but I'm happy to do this talk remotely. And I think lots of scientists all over the world are realizing, oh, I can collaborate with and talk to scientists anywhere in the world, and I can do it online on Zoom. And so I think in that way, we've got a nice thing that's happening in the past 6 months, is that people are realizing that they can form these collaborations around the world. So I would say to try to do that and build off of these interpersonal collaborations. I do see one more question that came up in the chat. What are the various disciplines that JPL works on except for astronomy? Well, JPL's biggest areas are planetary science. That is exploring the planets and the moons and the asteroids within our solar system. And then second biggest JPL effort is in earth science, studying the earth. And then after that, third biggest is probably astronomy.
Thank you very much, Jason. Let's see if anybody else would add a question or two. Well, you know, I'm sure people have a lot of things running in their heads with questions, but perhaps not ready to put everything.
Well, I'm always available if people want to send me an email. I can always try to answer questions over email as well. I'm very happy to do that.
Brilliant. That's very, very kind and generous of you, Jason. Oh, okay, everyone. I think it's a good time to wrap this up, and I think, you know, we've taken lots of energy from Jason answering questions almost without break. So thank you very much again, and I hope this inspires everybody to have seen how things work behind the scene in JPL. I think would give you lots of ideas of maybe getting things done in our country, you know, similar to that, and develop similar system. Lots to learn. Okay, so before we end, we have this tradition of having group picture. So if everybody would kindly turn on their video, please, so we could have a picture with everybody, and Jason could have a quick look of all of you. Okay, well, so who's going to take the picture?
Okay, I wanna take a picture for this session.
Excellent, thank you,
Okay.
Anton.
Please be ready for every participant. Okay, for slide 1, let me check. Okay. Okay, for slide 1, 1, 2, 3. Okay, second slide. Sorry. Okay, 1, 2, 3. Okay, thanks everyone.
Thank you, everybody. Now, before we end, please join me in giving Jason a really warm applause and thank for our expression of thankfulness. Thank you, Jason.
Thank you,
Jason.
Thank you so much, Jason.
Thank you so much.
Thank you so much.
So it was great fun. Thank you very much. Hopefully you can rest.
Thank you. Have a good day. Have a good school.
Yeah, for the participants, we'll be getting together again at 2 p.m. So have a nice break and make sure you rest some. Okay, everybody, good night, Jason. Thank you.
Thank you.